Hello everyone. So welcome to the live interactive session for week 5 of the course Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences at IIT Kanpur. And so I will be having these discussion sessions with you. And today's topic of discussion is problems on rheology. So this was the content for week 5, and we will proceed with this topic of today's discussion. So this is the basic outline of the course. So we started with basic concepts on structural geology. That was week 1, and then we moved on to measuring structural elements and how they are plotted in a stereographic projections. That was the content for week 2, and then we slowly started to enter the domain of deformation and the main causes or the main drivers of deformation. That was so first we learned how to identify strain. That told us, okay, so this is deformed and this is not deformed. So the distinction between deformation and something which is not deformed comes from the idea of the measurement of strain. So we already learned that in week 3's content. And the main cause behind this strain was, of course, um, obviously stress. So for week 4 we learnt about how stress plays a role in the deformation of a rock body especially. And now coming to the fact that at what condition of pressure, temperature and stress materials behave differently. So not only the amount of stress is important, but how fast or how slow that stress is being imposed, and how fast or how slow the material is deforming to the response of that stress is what we call as a broad topic of rheology of any materials and also for rocks. So rheology is a branch of mechanics that deals with the fact that a solid material or a fluid that is undergoing deformation under a continuum framework. So rheology, of course, deals with the fact that any material that is being deformed will be deformed continuously, and deformation should not be a discrete event. So that is the main drive of main proposition behind the subject of rheology. It essentially considers that any material, whether it is a solid or a fluid, crystalline, non-crystalline, amorphous, whatever it may be, the material is response is responding to the applied stress in a manner that the entire response or the deformation can be quantified via a continuum framework. The deformation event is not discrete, rather it is very much continuous, and there can be several variations in the response, or that is the deformation. Mostly we study how fast or how slow the deformation is responding to the stress if we change the rate of loading or rate of stress, temperature, pressure, and many other parameters like the fluid content, water content, and chemical composition, and so many other things. But the overall thing is that we try to understand how fast or how slow the material is responding to the stress. So that is essentially the fact of rheology. So we will discuss to them today in more details about rheology, and we will solve several different problems as we usually do in these live interactive sessions. And the main agenda will be to solve numerical problems related to rheology. Now, rheology essentially comes with certain theories about the mechanics of a solid, and every material has its own elastic constants that you have already learned in the week 5's content of this course. So we will mostly deal with these kind of facts, that how the elastic constant of a material would change if we apply pressure, if we apply temperature, if we introduce pore pressure into the system, how the effective stress would change, and so many other things that are mostly related to the mechanical parameters or mechanical properties of a material, right? So as usual, mm, this is the time for the live interactive session. It's the fifth week. Today is 22nd August of 2026, and we are hosting this live session from 5 p.m. to 7 p.m. and the live sessions are being hosted on each Saturday at the same time. So let us proceed with the content of this week's lecture. So to summarize what we have already learned and something that I have already talked about, so week 5's content mostly covers rheology, that includes the concepts of rheology, elastic, viscous and plastic deformations, classification of deformation processes in terms of rheology and internal cohesion, that is very important, application of rheology in our everyday life. Not just rocks, we do often subconsciously even apply the senses of rheology in our daily lives as well. And elastic constants of a material, concept of the generalized Hooke's law, concept of the stress strain diagram of a deforming material, then the concept of strain hardening, strain softening, and ideal plastic behavior of materials, linear viscous materials, combination of rheological models such as Kevin Voigt and Maxwell's models of viscoelasticity, something that involves elastic deformation and followed by viscous drag or something, and constitutive equations of viscoplastic material, application of rheology in geodynamics, effect of pressure, temperature, and pore pressure on the deformation responses of materials. So this is the entire concept. I know that it's a very large concept to cover within a single days of discussion, but I have designed several numerical problems that will be helpful for you know um, to connect more than two or three concepts together to solve these problems. So this is something that I designed for today's discussion. So we will be solving 20 to 21 numerical MCQ questions, multiple choice questions. I have also prepared the explanation for these numerical problems. So as usual, I will present one question to you, then I will pause for a minute or two. I will let you think what will be the correct answer to this question, and then we will be moving on to the next uh, question. So that's how the thing will proceed. And so today's goal is actually to solve conceptual problems related to rheology, stress and strain of materials, and some touches to geodynamics. Talking about stresses that are acting inside the earth, and how that the values are, and what is the strain rate of energy dynamic process, how they are being operated, and things like that. So And finally, we will summarize and conclude this live session for today's live session with solving these numerical problems. Okay, so that being said, let us start today's discussion session with the numerical questions. So, yeah. So the first question says a rock has a bulk modulus, that is K, which is 50 gigapascal, and Poisson's ratio nu, which is equal to 0.25. Now, assuming isotropic linear elasticity, what is its Young's modulus? We are denoting that Young's modulus with E. And the options are 25 GPa, 50 GPa, 75 GPa, and 100 GPa. So I will pause for a minute, and after that we will solve you know this problem. Okay, so the correct answer for this question will be option C, 75 gigapascal. Right? So now start with the explanation for these. So how to solve this, right? So for an isotropic elastic material, Young's modulus is related to the bulk modulus by this formula given that E is equal to 3 times K into 1 minus twice of the Poisson's ratio. So this is the formula we use for isotropic linear elastic material. So if the material behaves otherwise, that means either it is viscoelastic or viscoplastic with a non-linear elastic nature, then of course we will not be able to use this formula, and because you see that it essentially drives a linear equation in the form of y is equal to mx plus c, right? So or we can say that y is equal to mx. This is a very linearized equation. So a non-linear equation would generally involve a power law nature between the parameters like the Young's modulus and the bulk modulus, and this power law nature would generally bring an exponent, and that exponent will be related to the um, so that exponent would generally be related to the viscous component of of the material. So if it is a viscous material, viscoelastic material with certain amount of non-linear elasticity present, right? But for this problem, we are just considering isotropic linearly elastic material, and then we can obviously use this formula. So we have already been given these values, right? So the bulk modulus is 50 gigapascal. So we plug this value also with the Poisson's ratio. So if you just plug the values, we will generally get something like that. So the bulk modulus is 50 GPa and the Poisson's ratio is 0.25, and if we just plug the values, we will therefore get this kind of a numerical expression. So the Young's modulus will be 3 times 50 into 1 minus 0.50, because it's 2 times the Poisson's ratio, and that gives us Young's modulus is equal to 75 gigapascals, right? So this illustrates how elastic constants are interrelated and are not independent for an isotropic material. So for an isotropic material, every elastic constant, if you take the Young's modulus, and then you can easily relate that to with bulk modulus, the Poisson's ratio, the rigidity modulus, everything is related. So the first problem was essentially to relate the bulk modulus of a material with the elastic modulus, or the Young's modulus to be specific. Okay, so this was the first question that we have solved. Now we are moving on to the same type of question, where a rock has a Young's modulus of 70 GPa and a Poisson's ratio of 0.3. What is its shear modulus G, or the rigidity modulus, right? And so the options are 20 GPa, 26.9 GPa, 35 GPa, and 45.5 GPa. So these are the four options. And then again I will pause for a minute or two, and I will let you think what would be the correct answer to that. You can also solve yourselves, and after that obviously I will discuss so what formula we should use for this kind of a problem. Now before solving, I should mention that, like the previous problem as well, you should consider an isotropic linearly elastic material without any kind of a viscous dissipation or any viscous component, right? So if you consider a linear elastic material which is isotropic, then you can easily apply for a linear elastic formula. Okay, so let us solve this question. So the correct answer is option B, 26.9 GPA. Now the fact is that uh, the shear modulus is of course always more or less than the Young's modulus that you calculate. So as you can see that the Young's modulus was 70 GPA, and from that we derive a shear modulus of 26.9 GPA. Now here's the explanation for this question. So again, for an isotropic linearly elastic material, the shear modulus is given by G is equal to E upon 2 into 1 plus nu. So that's how it relates the formula. This formula relates the shear modulus with the elastic modulus, I mean the Young's modulus, and the Poisson's ratio. Right? So from that we now substitute E, which is 70 GPA, and the Poisson's ratio, which is 0.3, gives this relation, numeric expression, and the denominator in this case is 2.6, and therefore we get a value of nearly 26.9. So the shear modulus therefore measures the material's resistance to shear deformation. So if we know that by definition the elastic modulus, which is the Young's modulus, so Young's modulus essentially reflects the resistance to axial deformation, axial compression or tension, whatever, and rigidity modulus on the other hand, or the shear modulus, describes the resistance of a material to shear deformation. Right? Okay, so this was question number 2. Now let us move on to question number 3. So this relationship between, there are several components, like there is a bulk modulus, there is a Young's modulus, and there is a rigidity modulus. So all these are essentially the components of the generalized Hooke's law framework. So one can actually derive from the generalized Hooke's law, one can actually derive interrelations between different kinds of elastic moduli. Okay, so now that so the first two questions were essentially related to the elastic limit of a material undergoing deformation. Now we are heading to something, we are talking about plastic deformation of a material, and whenever we are talking about plastic deformation, there can be three general kind of behavior that we can see from a material that has just crossed its yield point. Right, so now the elastic domain is complete, I mean it has undergone the elastic deformation, now it is entering the plastic domain or the ductile deformation domain, where it has just crossed its yield point, and beyond that point there can be generally three types of deformation, or the response of the deformation can be of three types. One can be strain hardening response from the material, and one can be a strain softening response, and the other one is the generally ideal plastic response of a material. So that whether the material is strain hardening or strain softening, that would depend on the response in the stress strain curve. So post yield, after the material yields, if it takes higher amount of stress to increase the strain for an unit amount, than that was previously for the I mean, uh, when the material was yielding. Say for example, the yield point is essentially the stress or and the strain at which the material shifts from elastic deformation to plastic deformation. And post yield means that the material is now undergoing plastic deformation. So any kind of deformation that we are talking about, any kind of strain is now inelastic strain or permanent strain, right? So if the stress keeps on increasing, I mean, if the requirement of stress to impose a unit amount of permanent strain in the material keeps on progressively increasing or monotonically increasing, then that behavior would be coined as or the termed as a strain hardening response from the material. Now, on the other hand, if the opposite happens, is that the the requirement of stress to, you know, impose unit amount of permanent strain into the material keeps on decreasing post yield, then that response will be called as a strain softening response from the material, strain softening material. And if there is no change in the stress, like post yield, if the stress remains more or less constant, to I mean, you do not need further enhancement in the stress to accumulate permanent deformation inside the material, that kind of a behavior would be called as an ideal plastic deformation, right? So the problem is following that theory, and it says that a rock mass follows a strain hardening relation. Sigma, which is the stress, is equal to K times epsilon to the power n, where K is some constant which is an unit of stress, it's 120 MPa, and n is 0.5. This is the strain hardening exponent. So what strain is required to reach a stress of 30 MPa? Now remember that this relationship holds post yield. That means whatever be the case, the material's yield stress maximum limit will be 30, not beyond that. I mean, that's for sure. We can say that anything but the stress, yield stress, would be less than that, less than 30. What we can say, definitely, or maximum 30, right? So everything happening here is post yield. So definitely the yield strength of the material is either 30 or even less than that. Now the options given are 0.0156, that means 1.5%, 2.5%, 6.25%, or 12.5%. So these are the different options given in strain. So if post yield, if it requires 1.56% of strain, or it requires 2.5% of strain, or 6.25% of strain, or 12.5% of strain. So the formula is already given. You will just need to do some algebraic manipulation and calculate the value of epsilon or the strain and match with the given options. So I will pause for a minute and I will let you solve these numerical problem, and then we will discuss in detail. Okay, so let us see how this has been solved. So the correct answer is C, 6.25% of strain. Now to give the explanation, of course the strain hardening relation is given, sigma is equal to K times epsilon to the power n. Now with sigma is equal to 30 MPa, K is equal to 120 MPa, and n is equal to 0.5, we just plug all the values in and we get these numerical expression, and therefore E epsilon to the power 0.5 is 0.25, and then obviously we take squares both side to give epsilon is equal to 0.0625, thus a strain of 6.25 is required, and the positive exponent indicates that the flow stress increases with increasing strain, which is the characteristics of strain hardening, right? Okay, so this was about post yield behavior. So now let us move on to the next question, which is question number 4. So which stress strain response best represents an ideal perfectly plastic material after yielding? Option A, stress continues to increase with strain, stress decreases continuously with strain, stress remains approximately constant as strain increases, and stress becomes zero immediately after yielding. So these are the 4 options given for question number 4, and that's something we already discussed while solving question number 3 about the post yield response of a material, right? So we generally see 3 types of material: strain hardening, strain softening, and ideal plastic behavior, and the question is related to that. So I will let you think for some time and then we will solve this question. Okay, so let us solve. So the correct answer is option C, and that is stress remains approximately constant as strain increases. right? So option C is the correct answer. And what is the explanation behind this answer? So an ideal plastic material exhibits a distinct yield stress. Once the yield point is reached, additional permanent strain can occur without a significant increase in stress. Right? Thus, the post-yield portion of the idealized stress strain curve is approximately horizontal. Now, this differs from strain hardening, where stress increases with accumulated strain. It also differs from strain softening, where the required stress decreases after yielding. So, an ideal plastic behavior is therefore represented by an approximately constant flow stress after yield. So, that was about so this was about so the previous question was about strain hardening, and this was about an ideal plastic material. So for an ideal plastic material, essentially the yield stress is equivalent to the flow stress. But for a strain hardening material, that won't be the case. For a strain hardening material, the flow stress will keep on increasing. So the flow stress essentially becomes the differential stress after the yield. So if you calculate the differential stress, that is sigma 1 minus sigma 3, after the yield point, then that becomes the entire stress becomes your flow stress. So for a strain hardening material, the flow stress will keep on increasing. For a strain softening material, the flow stress will keep on decreasing, and decreasing with respect to the yield. That's very important to note, that post yield phenomena are always calculated with respect to the yield point. Right? For any material which shares a strain hardening component within its stress strain curve, the ultimate flow stress where the deformation is stopped would likely be less than the yield strength, greater than the yield strength of the material, or the yes. But for a strain softening material, the point at which the flow has stopped, the final flow stress would likely be less than the yield strength of the material. And that's how we define three different kinds of response. Okay, so coming to the question number 6, it says that a Maxwell material consists of a spring with Young's modulus 1 into 10 to the power 11 Pascal and a dashpot with viscosity of 2 into 10 to the power 21 Pascal second. What is its characteristic stress relaxation time? Option A, 2 into 10 to the power 8, 2 into 10 to the power 10, 2 into 10 to the power 12, or 2 into 10 to the power 30 seconds. Right? So now we are entering the viscous domain, viscous deformation. So this obviously happens post yield. We're talking about something related to the von Mises criteria of a flow, material that is flowing, and also it shows viscous component in the deformation. Okay, so it's a little bit of different than what we were solving previously. So I will pause for a minute or two and I will let you solve and think about this question, and then we will solve together. So which option will be correct, we will see. Okay, so the correct option is option B, that is 2 into 10 to the power 10 seconds, right? So if we go to the explanation, for a Maxwell model, the characteristic relaxation time tau is essentially the ratio between the viscosity and the Young's modulus, right? So here the viscosity is 2 into 10 to the power 21 Pascal second, and the elastic modulus given here, the Young's modulus, is 10 to the power 11 pascals. That means it's nearly about 100 GPa, 100 gigapascal, right? So therefore, if we plug in the values, we will get the relaxation time 2 into 10 to the power 10 seconds. So the relaxation time indicates the characteristic time scale over which the stored elastic stress decays. So it indicates that a material that follows a Maxwell geology was deformed to a certain stress, and then stress relaxation is happening. The the strain is held at that point. The deformation is held at that point. Now the stress is slowly relaxing. So it's not a strain decay model; it's a stress decay model, right? So it is a form of creep, but then it involves relaxation of stress. Okay, so now we should move on to the next question. And actually, a large viscosity therefore produces a long relaxation time and more persistent stress, and that's for sure, right? And it also depends on the elastic modulus of the material. The more elastic modulus a material has, it's more stiff, and that would mean that it has a higher viscosity. And if you take the effective ratio between the viscosity and the elastic modulus, it would generally indicate the relaxation time would be higher for any material having such high elastic constants, right? Okay, so now moving on to the next question. A Kevin Voigt material has Young's modulus E of 20 GPa. Now, if a constant stress of 100 MPa is applied for a long time, what strain does the material approach asymptotically? Right? And the options are 0.05% or 0.05, 0.25, 0.5, or 5 different percentages of strain. Right? Okay, so I will pause for a minute and then we will solve this question together. Okay, so the correct answer is option C. And how we calculate that? Now, in a Kevin Voigt model, the spring and dashpot are arranged in a parallel combination, not in a series. So, under constant applied stress, the strain approaches the elastic strain at long times. And the elastic strain is simply the ratio between uh, the stress and the elastic modulus or the Young's modulus. And so simply we take the ratio which is 100 MPa divided by 20,000 MPa, and the option is 0.005. That means the asymptotic strain is 0.5%. So in a Kevin point model, if you held the stress constant, the strain will relax and it will eventually try to come up to its elastic strain. So it will try to recover, right? And this recovery will take only up to the elastic limit. And the elastic limit is therefore can be calculated from simply by applying the Hooke's law, right? And from the Hooke's law we can calculate the strain is equal to the ratio between the applied stress and the Young's modulus, right? So the dashpot controls the rate of approach while the spring controls the final equilibrium strain. So what will be the final strain that is dictated by the spring, but the rate of deformation is it is controlled by the dashpot, because ideally a spring which is elastic is rate independent. It should not depend on the rate, but it should be the function of only the final and initial strain, right? So that's why the time component does not come from the spring, but it comes from the dashpot, because it's a viscous component. Okay, so this was question number 6, and so let us move on to the next question, which is question number 7. And again we are discussing about linear viscous material. So a linearly viscous rock deforms at a strain rate of 1 into 10 to the power minus 13 per second under a differential stress of 50 megapascal. So what is its effective viscosity, eta? And the options are 5 into 10 to the power 16 pascal second, 10 to the power 18 pascal second, 10 to the power 20 pascal seconds, or 5 times 10 to the power 22 pascal seconds. So again I will pause for a minute and then we will quickly solve this numerical problem. Okay, so the correct answer is option C, which is 5 times 10 to the power 20 Pascal seconds. And for the explanation, a linearly viscous material stress is proportional to the strain rate, right? And so does the simple constitutive equation is that eta viscosity is equal to sigma divided by epsilon dot, which is the strain rate. Now we can easily have the value of 5 times 10 to the power 7 pascals for the stress of 50 pascal, 50 megapascal, and then we simply put the value, right? We were been given the strain rate of 10 to the power minus 13, and so does this stress, and that gives us the viscosity of 5 times 10 to the power 20 pascal second, right? So thus the material has a very high effective viscosity typical of slow geological deformation. So this is the range we generally talk about, because even though the stress of 50 MPa is quite natural quite achievable in natural conditions, this is the characteristic strain rate that we generally observe in geological processes, that we generally consider as creep, right? And this kind of strain rate is not achievable in laboratory experiments, because we simply do not have that much time to deform a rock in such a slow rate and to observe the microstructures. Yeah, that's not actually possible. So I mean, these kind of strain rates generally operate in natural condition, and that's why the effective viscosity of a rock is so high, right? Because of the strain rate. So had it been the strain rate was higher a bit, like 2-3 orders of magnitude, and simply we could achieve those kind of viscosity in laboratory experiments, and that would be the lower bound of the strain rates that are still achievable in laboratory condition of deformation. Okay, so move on to the next question. Question number 8. So a porous rock is subjected to a total mean stress of 120 megapascal, while the pore fluid pressure is 40 megapascal. So what is the effective mean stress? Option A 40 megapascal, option B 60 megapascal, option C 80 megapascal, and option D 160 megapascals. So you have to apply the effective pore pressure theory to deduce these problems. So we solved these kind of problem in the last week as well, related to the pore pressure. So I hope that you can reconcile that equation and can apply that here as well. Okay, so I will pause for a minute and let you solve, and after that we will solve this numerical problem together. Okay, so correct option is option C. And to explain this question, effective stress accounts for the reduction in total load carried by the rock framework due to pore fluid pressure, right? So the effective stress is essentially the difference between the given compressive stress and the pore fluid pressure. So the total mean stress is 120 megapascal and the pore pressure is 40 megapascal. So we simply subtract, and that is the effective mean stress. So increasing pore pressure at constant total stress would therefore reduce effective stress and generally facilitate deformation or failure. So that's the role of pore pressure, to actually reduce the effective stress, right? Okay, so this was easy, question number 8. Now, so let us move on to question number 9, and that is a standard question. Like, so we have been given that rock has a density of 2,700 kilogram per meter cube with acceleration due to gravity 9.81 meter per second square. So what lithostatic pressure is produced at a depth of 8 kilometers? And the given options are 21.2, 105.9, to 11.9, 423.8 megapascals. So these are the options, and it won't take you more than a minute to actually solve this question, because we have already solved this kind of numerical problems from week 1. It's a very common problem. Okay, so the correct answer is option C, 211.9 megapascal. And the explanation is simple, because the lithostatic pressure can be approximated by P is equal to rho times G times H for a uniformly dense column, right? And here it's 2700 kilograms per meter cube with G is as usual 9.8 per meter per second square, and the the depth can be converted to meters, that is 8,000 meters. Now we plug these values and calculate the value in terms of Pascal, and the result is 2.119 times 10 to the power 8 Pascal, and therefore it is equivalent to 211.9 megapascal, or roughly around 2.12 kilobar, right? So this demonstrates how pressure increases with depth and contributes to the deformation environment within Earth, right? Okay, so let us head on to the next question. Yeah, so for a uniaxial elastic deformation, a rock with Young's modulus of 75 gigapascal is subjected to an axial stress of 150 megapascal. What axial strain results in this deformation? Option A 0.02%, option B 0.1%, option C 0.2%, option D 2%. Right? So think for a minute and then we will solve this question. Okay, so the correct answer is option C 0.2%. And the explanation is that according to Hooke's law, the stress and the strain are and the stress and the elastic strain are related with an elastic constant, which is the Young's modulus in this case. And we just do simple rearrangement, sigma by E, and the given values of stress is 50 MPa, 150 MPa, and elastic modulus is 75 GPa, that means 75,000 MPa, and we plug all these values together to get the value, and that means the resulting axial strain is therefore 0.2%. So this calculation illustrates the proper proportional stress strain responses within the elastic regime. So that is very important because we are studying the elastic deformation. So if it's already, so if the stress 150 MPa was beyond the yield point, we generally could not apply the the Hooke's law of elasticity, right? Okay, so moving on to the next question. So an isotropic material has Lami's first parameter lambda is equal to 20 GPa and the shear modulus G is equal to 30 GPa. If the x direction strain is 0.01% and the y and z direction strain are equal and all are 0.05%, then what is sigma x according to the generalized Hooke's law given in the form sigma x is equal to lambda times epsilon x plus epsilon y plus epsilon z plus 2 into g into epsilon x, right? And the options are 60, 80, 100 and 120 MPa, right? So all these values are given. So you simply have to plug these values in the equation of the generalized Hooke's law with the first Lami's parameter is given here in this question. You just use this formula to calculate the value of the differential stress acting along sigma x. Now the material is isotropic, so therefore the section that we are talking about where sigma y and epsilon y and epsilon z are equal, so the correct answer is option C, 100 MPa, and the explanation is that we simply take the isotropic three-dimensional elasticity. Already the formula is given, that is so now the first parameter for the Lami's equation, we are considering isotropic material. If not, then there will be three different constants, excuse me, three different constants depending on the direction, right? And we plug the values here. So the sum of the strain is 0.02%, and the first term is, therefore you just plug these values, is 0.04 GPa. Second term is of course 0.06 GPa, and then finally if you add them up it will give 0.1 GPa, which is 100 megapascals, right? And so this demonstrates the generalized Hooke's law for coupled three-dimensional deformation, and this is the most easier version that you are seeing because already we have considered an isotropic material. So had this been an anisotropic material, it would have been very difficult, and the generalized Hooke's law would be much more extended than this one. Okay, so we shall move to the next question, question number 12. So the question number 12 says that for a Maxwell type viscoelastic material, which response is most characteristic when a constant strain is suddenly imposed and then held fixed? Now think about it. It is talking about an impact, right? An impact followed by held fixed means you are adding an impact strain and then you are holding that strain constant. So what will be the consequences of these event? Option A, stress remains constant forever, stress gradually relaxes with time, strain immediately returns to zero, and stress increases without any limit, right? Now we have already discussed Maxwell type viscoelastic rheology in earlier problem today, so I hope from those discussion you can solve this this conceptual question, and it is easy. We already discussed the consequences, what happens when we put strain in a Maxwell rheology, right? So in Kevin Voigt rheology, we generally talk about stress as the input parameter, right? But in a Maxwell rheology, we talk about strain as the input parameter, right? So these are the two main differences between these two rheological models. Okay, so think what will be the correct answer. Okay, so the correct answer is that the stress gradually relaxes with time. So we already solved this question about the relaxation time. It's the ratio between the viscosity and the elastic modulus, right? So that's how we calculate the relaxation time in a Maxwell type rheology. So to explain this, a Maxwell material combines an elastic spring and a viscous dashpot in series, not in parallel, right? Whereas in Kevin Voigt rheology, those are in parallel combination. When we talk about Maxwell rheology, it's generally in series, right? So when a constant total strain is imposed, the initial response contains an elastic stress because the spring is hit first. So its deformation is instantaneous, right? It's not rate dependent. With time, the dashboard deforms and the stress carried by the spring decreases. So strain stress is being partitioned between the spring and the dashboard, and so this produces a stress relaxation, right? And the rate of relaxation is controlled by the characteristic relaxation time tau, which is the ratio between the viscosity of the deforming material and its elastic stiffness, right? So if it's an axial deformation, then we should consider the um, Young's modulus, and if it's a more of a shear deformation, then we should consider the rigidity modulus and so on, right? And so the Maxwell behavior is therefore useful for describing time dependent relaxation of stress in geological materials like post seismic relaxation or glacial upliftment and relaxation after glacial meltdown. So these kind of phenomena are generally described using the Maxwell rheology model, right? Okay, so moving on to the next question, question number 13. So in a multi-layered rock undergoing shortening, layer A has a much higher viscosity than surrounding layer B. So which behavior is most likely if both layers deform viscously? Option A, layer A preferentially accommodates flow and becomes the least competent layer. Option B, layer A behaves as the more competent layer and tends to resist deformation relative to B. Option C, both layers must deform identically regardless of viscosity. And option D, layer B must always fracture while layer A remains undeformed. So these are the four options given, and I will let you think for some time and then we will discuss, because this has to be answered in terms of the competency contrast between different layers. So you have already gone through this. Recall how fold and boudinage are being formed, right? And these examples are already given in your lectures. Okay, so the correct answer is option B. Layer A behaves as the more competent layer and tends to resist deformation relative to B, right? So yeah, obviously the deformation ultimately is a function of the viscosity contrast between multiple layers when there is a multi-layered rock undergoing deformation, right? And that actually introduces heterogeneity in deformation. So the heterogeneous deformation do arise from these perspectives, that there can exist competency contrast between different layers, and therefore different layers would accommodate the strain differently than each other. So the explanation is that viscosity measures resistance to viscous flow. It's simple, right? But then a layer with higher viscosity requires greater stress to achieve the same strain rate. And therefore layer A is mechanically more competent than the lower viscosity layer B. So during shortening, the viscosity contrast promotes strain partitioning between different layers. It's obvious. And the weaker layer can accommodate more viscous deformation while the stronger layer resists the flow. And such rheological contrasts are important in understanding folds, boudinage, and pinch and swell structures in the field, right? So the relative competence of different layers would actually dictate whether a same configuration would undergo folding or boudinage or pinch and swell structure. Same configuration, same composition in fact, but the competency contrast can switch and therefore do the deformation mechanism as well, right? Okay, so this was question number 13. So let us move on to question number 14. So a material shows decreasing apparent viscosity as shear rate increases. Which rheological behavior is most consistent with this observation? Option A, shear thickening. Option B, shear thinning. Option C, perfect elasticity. And option D, ideal plasticity. Right? So there are 4 different options. So I will pause for a minute and let you think. It's a tricky question. Okay, so the option B is correct, shear thinning, right? And to explain that, apparent viscosity describes the ratio between stress and strain rate for a non-Newtonian material, right? That is for shear. So if apparent viscosity decreases as shear rate increases, the material is localizing the deformation, so therefore it is a shear thinning material, right? And this is of course a non-linear and therefore non-Newtonian viscous response. So in contrast, shear thickening behavior involves increasing apparent viscosity with increasing shear rate. Neither ideal elasticity nor plasticity is defined primarily by this viscosity shear rate relationship, because both of them are rate independent. Okay? Only viscous deformation is rate dependent. So that is why option C and option D are eliminated, and option B is more towards hardening phenomena, and option A is more towards a softening phenomena, right? So thus decreasing the viscosity with increasing shear rate indicates shear thinning, a phenomena that can also be correlated with the strain softening phenomena, right? Okay, now moving on to the next question. So a viscoplastic material follows the simplified Bingham relationship, which is defined as the strain rate is equal to the differential stress divided by the viscosity, where of course sigma is greater than sigma y, which is the yield stress, right? So we are essentially talking about the flow stress, right? So so if sigma y is 60 megapascal and the viscosity is 10 to the power 20 pascal second, and the normal stress is 110 megapascal, what will be the strain rate? So it is very simple, you just plug in the values and calculate the values, right? And the options are 5 times 10 to the power 15, sorry, minus 15 per second, 10 to the power minus 13 per second, 1.1 times 10 to the power minus 12 per second, and 1.7 times 10 to the power minus 13 per second, right? So what? So the thing is that the formula is given, and it is essentially the formula of, you know, defining the viscosity. So viscosity is defined by the stress by divided by the strain rate, right? So if you just plug in the values, you will see that option B is the correct answer, which is the strain rate is 5 times 10 to the power minus 13 per second. And to explain this, for the simplified viscoplastic relation, the excess stress above yield drives the viscous flow. Yeah. So the excess stress is 50 megapascal. Now convert that to pascals, it's 5 times 10 to the power 7 pascal, and just simply plug in the numerical values to obtain the value of strain rate, and it is near to 5 times 10 to the power minus 13 per second. So the material therefore behaves elastically or rigidly below yield and flows progressively once the yield stress is exceeded, right? So it's a viscoelastic behavior. Okay, moving to the next question. So an earthquake rupture has seismic moment 2 times 10 to the power 18 Newton meter. The rupture area is 100 kilometers square. The average slip distance is 0.2 meter. So what is the rigidity modulus in this case if the material is failing? So the options are 10 to the power 8 pascal, 10 to the power 9 pascal, 10 to the power 10 pascal, or 10 to the power 11 pascal. Right? So I will pause for a minute, let you think. Okay, so the correct option is D, 10 to the power 11 pascal, that means 100 GPa. And the explanation is that the seismic moment is related to the rigidity modulus, rupture area, and slip by this formula. Moment is equal to modulus times area times slip. So the area is equivalent to 10 to the power 8 meter square, and rearranging the terms give us the value of rigidity modulus, moment by area times slip. So it's, we are actually giving a dimension of volume, right? And so you simply calculate them and you get a ratio of this numerical expression, and then the rigidity modulus is therefore 10 to the power 11 Pascal. So this links earthquake source parameters to the elastic shear properties of the deforming rock. So one thing is that if we know beforehand what is the elastic properties of the rock, we can have an estimate how much moment can be released for certain amount of earthquakes, and that can actually help us to go for a prediction of earthquakes kind of thing, right? So we know the damage from these parameters. Okay, so moving on to the next question. So using rigidity modulus now, it can either be defined as or termed as mu, or it can also be written by G, doesn't matter. So we have a rigidity modulus of 10 to the power 11 pascals, and given from the previous problem, and we have the density of the rock 2800 kilograms per meter cube. What will be the shear wave velocity if an earthquake do occur for that rock? And the options are 1890 meter per second, 3780 meter per second, 5980 meter per second, or 8400 meter per second. Okay. The correct answer is option C, 5980 meter per second. And the explanation is that the shear wave velocity is related to rigidity and density modulus by this formula. Vs is equal to under root G by rho. And so simply plugging in the values, we get this numerical expression under root 10 to the power 11 divided by 2800, and the ratio is approximately 3.571 times 10 to the power 7 meters square per second square, and taking root of these expression gives us 5976 meter per second. So rounded suitably, the shear wave velocity is about 5980 meters per second, and this demonstrates the connection between elastic properties, density, and seismic wave propagation, right? Okay, so moving on to the next question. A rock has axial strain 0.02%, 0.2%, and Poisson's ratio of 0.25 under uniaxial loading, right? So what is the magnitude of the transverse strain? Okay. And these are the options, and the correct option is option B, which is 0.05% of strain. So if we give the explanation, so for uniaxial elastic deformation, Poisson's ratio nu is defined by the negative of transverse by axial strain, right? And if you just take the have to take the magnitude, we eliminate the negative sign. So if we simply multiply the Poisson's ratio with the axial strain, we get the transverse strain, right? And thus the transverse strain is 0.25 times 0.0002, so which gives us 0.0005, and that means the transverse strain has the opposite sign to the uniaxial strain during conventional uniaxial compression or extension. And so this behavior illustrates the coupling between deformation components in an elastic material, because the thing is, for a same density material, the volume has to remain constant. So that is the main so it's a main component behind understanding how the Poisson's ratio works. right? Okay, so here we have been given an expression. So a rock has an initial yield strength of 120 megapascal. Suppose its simplified strength relation is sigma y is equal to 120 minus 0.1 t plus 2p minus p suffix p. So where is, so p is the, t is the temperature, and these are pore pressures and confining pressure. So what will be the sigma y, the yield stress, if the temperature reaches 200 degrees centigrade with a 10 megapascal increase in pore pressure while staying at a confining pressure of 20 megapascal. And so the options are 80, 100, 120 and 130 megapascal, right? So the correct answer is option D. And for explaining, so this is an empirical relation, combines the temperature, confining pressure, pore field pressure with the yield strength, right? So we simply substitute the values, 200 degree pore pressure and the confining pressure in the equation given, and the temperature contribution is minus 20 megapascal, pore pressure is minus 10 megapascal, and thus simply adding all these components together we get an yield strength of 130 megapascal. So therefore the correct numerical result is 130 megapascal. So yeah. Okay. Question number 20 says that which everyday example is most clearly illustrates a time dependent rheological response rather than purely elastic behavior? Option A steel spring returning rapidly to its original shape, a glacier slowly flowing under its own weight, a quartz crystal undergoing instantaneous elastic strain, and a rigid block translating without deformation. So it's obviously very easy. So the answer will be option B, a glacier slowly flowing under its own weight, right? So if we explain, a time dependent rheological response means that deformation depends on the duration and rate of loading, right? So glaciers deform and flow slowly under sustained gravitational stress. So this behavior is therefore strongly viscous or viscoplastic rather than purely elastic. A steel spring is commonly used as an idealized example of elastic behavior. Quartz can also show elastic deformation over short time scales. So these are generally related with the piezoelectric behavior of quartz. But glacial flow demonstrates why rheology is useful for connecting material behavior to large scale geodynamic processes, and it is essentially a viscous deformation mode. Right? Okay, so coming to our last question of this session. So a material undergoes stress relaxation after being rapidly strained to a fixed total strain. Which rheological model is most directly associated with this kind of behavior? Option A, Maxwell model. Option B, Kevin Voigt model. Option C, purely viscous models only. And option D, purely plastic models only. And since we have been discussing all these numerical problems related to Maxwell's rheology or Kevin Voigt rheology, we can obviously say the correct answer is A, option A, which is the Maxwell's model. And to explain, we can say that the Maxwell model consists of an elastic spring and a viscous dashpot arranged in series. So under total fixed strain, the viscous element can continue to deform with time, So as the dashboard deforms, the stress carried by the spring it decreases. So this is the process of, so this produces a stress relaxation, a defining behavior of the Maxwell model. Whereas the Kevin Voigt model is more commonly used to describe delayed creep under suddenly applied constant stresses, a transient strain rather than a transient stress. So a transient strain is a Kevin Voigt response, a transient stress is a Maxwell response. So therefore, Maxwell model is the appropriate choice for stress relaxation. So, okay, this is the final question we have solved. And so, with this, I end the week 5's discussion related to the problems regarding rheology. So, in the coming week, we will discuss about the deformation mechanisms of minerals, more specifically talking about crystal plastic deformation and different kinds of deformation mechanism, and we will solve some conceptual MCQ problems related to those topics. So until then, bye.